Hello and welcome everyone to the next event in our webinar series, a presentation by guest speaker Bill Diamond, President and CEO of SETI Institute in Mountain View, California. My name is Michael Mohammadi and I will be moderating today's webinar. The SETI Institute is focused on the study of life in the universe. SETI is a nonprofit astrophysics and astrobiology research and education organization. I'm very excited to have Bill join us today, as I've personally been a big fan of SETI since I was a little kid. Many of us have we grew up inspired by the movie Contact. My love of SETI really took off in 2005 when I visited the now closed Arecibo radio telescope. I still have an Arecibo coffee mug that I use every day. It's a constant reminder that science should be both fun and wondrous. Today, Bill will give us an update on what's new and exciting at SETI. We will learn about the science and innovation happening beyond just the search for extraterrestrial or other life in our universe. A little bit more about Bill. Bill Diamond might have the coolest job in California. He is the current president and CEO of the SETI Institute. He completed degrees in physics from Holy Cross, as well as an MBA from the Georgetown McDonough School of Business. He's a Silicon Valley technology veteran, having held various executive management positions in applied technology, including CEO at WaveSplitter Technologies, Dennis Light Semiconductor, and X-Radia. Most recently, he was vice president of product management at the optical communications company Aclaro. Bill has over 30 years experience in laser photonics, optical communications, and X-ray imaging, as well as semiconductor processing technologies. We're extremely lucky to have him join us today. We were actually really excited to have Bill join us in our headquarters in Newton, New Jersey, but unfortunately a snowstorm kept many of us working remotely. Throughout Bill's talk, feel free to submit any questions you might have using the Q&A tool. He will be answering the questions at the end. Bill, thanks again for joining us today. The floor is all yours.
Great. Well, thank you very much, Michael. Thank you for that kind introduction, and wonderful to not see you all. But I sense your presence thanks to the technology we have at the Institute. And by the way, if you hit that little button on the screen that allows you to minimize our presentation, I'll know who you are. No, I'm kidding. But anyway, it's great to have this opportunity. What a wonderful series and a wonderful thing that Thorlabs does to provide platforms like this and opportunities for all of you to meet and hear from different people in different walks of life doing interesting things. So I will say that where Michael made reference to my job as the coolest job in CEO in California, I don't know about that. What I do know, I describe myself this way, and I think it's accurate. I have the coolest and least lucrative CEO position in all of Silicon Valley. So that's the executive summary. In any case, I'm here also because a dear friend of mine and somebody who's been a colleague of mine over many, many years, KR Subramanian, is at Thorlabs now in the DC office, and hopefully somewhere in this audience today, because it was KR that got me connected to Thorlabs in the first place, for which I'm very grateful. So without further ado, let me jump in and tell you a little bit about the SETI Institute, what we do, and how it all works. So let me see if that button does something for me, or maybe that one. Yes, here we go. So in terms of the search for life and intelligence beyond Earth, what we're going to talk about today is how it works. What are the tools and technologies we use to do this, take on this endeavor, where things stand, what have we learned, what have we discovered, what is the current state of the art, both in terms of technology and results, and why it matters. I think impact and meaning are also quite important here. And in terms of where it stands, some people will often ask me, one of the favorite questions is, have you found anything yet? To which I answer, if we'd found something, you'd probably know by now. So we have interesting discoveries. We've learned a lot over the past few decades that make the search, I think, only more compelling with each passing year. We obviously haven't discovered life beyond Earth. why that's such a daunting undertaking. So you'll get a sense of the endeavor over the course of this talk. What are big questions behind what we do at the Institute? Sort of what are the driving fundamental research areas of inquiry behind us? And the first is, how does the universe work? Starting Big Bang. And this is all about the cosmos. So this is about galaxy formation, star formation, I'd say precursors to life that we believe are probably abundant in the universe. And then the second science question is, how did we get here? So how did life happen on Earth? What are the conditions necessary for life? What were conditions under which life began, what we call the origins of life? And we don't yet know, honestly, how life started. I think we're getting closer and closer to an understanding of that. Have the conditions that led to life here on our planet arisen elsewhere in the universe? Do they exist elsewhere? And if that's the case, might life have taken hold and hopefully evolved on other worlds? And if that happened, can we find it? We find evidence. So interestingly, you might think, oh, these are the SETI Institute questions. Well, they are actually top 3 questions. So if you go to Google, type in what are NASA science questions, these are their science. And I would say more frequently now than ever before, almost invariably scientists and talking about the purpose of their work, they'll almost invariably question, are we alone? Because ultimately, I think all of us, whether we're at NASA or academia or institutes like ours, this is ultimately what we're trying to figure out. So that's the question, are we alone? And what's interesting about this question is presumably, as old as human beings, as old as, the first stared up at the sky on a starry night and had an opportunity to wonder what they were looking at, what they were seeing, and if there were others like themselves up in that sky. And so, but honestly, for the vast majority of human history, 99.999%, this question has been confined to the realms of religion and philosophy and not a science question. But that has changed now. For the first time in our history, we actually have the tools and technologies to find out, to answer that question. So a little background before we get into how does it work, just a little bit of background about the Institute. So the Institute, our mission statement is to lead humanity's quest to understand the origins and prevalence of life with the world. And that second part of the mission statement is as important as the first. We're a 501c3 nonprofit. Much of our work is government-funded research from grants, cooperative agreements, and as such, those government-sourced funds are coming from you and me, from the taxpayer. So we feel it also is a social responsibility to give back, to let everybody know what we're up to and what kind of work we're doing, what kind of results we're getting. So sharing the work is. But the other thing that I think stands out slightly in this mission statement is it's not just about life. So much has been spent by NASA and others to look for life in its most basic forms, primarily in our own solar system. So we'll talk more about that later. But intelligent life is life that might a technology transmitted either intentionally or accidentally that we might be able to observe, or what we call technosignature, some indication of life and intelligence beyond our solar system would be a pretty indicative, I'd say, measurement or observation of life and intelligence. So this would be technology as a proxy for life and intelligence. So we're very interested in. So of activity, we have the Carl Sagan Center for Research, which is where we do our science and exploration. We have the Center for Education, where we have educational programs. Hopefully those later. And then we have our outreach programs, which is all about public engagements, a little bit like your teams. The scientists and staff at the Institute are all passionate explorers and scientists. We call them kind of explorer scientists because very often, for those who work in the field, which is some of our scientists, they're going to the far corners of the earth and they're undertaking activities in environments that are extraordinarily harsh and in many cases very dangerous. So they truly are explorers, but they go to these places and do some of the things they do, not because they're trying to be heroic or actually, do something crazy, but rather because it's required for their science. Our scientists, again, are all professional scientists and researchers. So rigorous science is a key element of the work we do. It was the mathematician Laplace who famously said, and it was sort of borrowed by Carl Sagan, extraordinary results require extraordinary evidence. And so, building evidence for the work we do is all about doing so on a foundation of hardcore science. So that's our team. Some facts and figures about the Institute. We're founded in 1984. So actually this is our 40th year. We were founded by an astronomer, Jill Tarter from Cornell University, who's a colleague of Carl Sagan's, and Tom Pearson at the NASA Ames Research Center. The Institute was born out of NASA Ames, where the first SETI experiments were being funded and conducted there. And Michael mentioned the movie Contact. For those of you who are familiar with that movie, starring Jodie Foster, playing a character named Ellie Arroway, that character was written into the book by Carl Sagan based on Jill Tarter. And so the beginning of the movie, where the young radio astronomer Ellie Arroway is at the Arecibo Observatory, where Michael said he visited, and it was quite something to see before it collapsed. That's all of the work that Jill and her colleagues did. So like half the movie is Jill's biography, the other half of the movie is science fiction. So in any case, that's Jill. She's quite a remarkable woman. She's still on our board of trustees, retired from active research, but one of a pioneering woman astronomer who became an astronomer at a time when women weren't even allowed in observatories. So it was a different time. Let me just ask you now, how's the audio, Michael? Is it okay?
It's perfect. Thanks, Bill.
Okay, great. All right, so we have more than 90 PhD research scientists. I guess now we're approaching 100. And we also have research affiliates who submit proposals for funded research through the Institute and hope to become funded and join the permanent team. We have more than 20 separate research domains covered by Institute scientists. So that means we're covering almost all the natural sciences. We have biologists, microbiologists, chemists, physicists, astronomers, astrophysicists, geologists, planetary geologists, data scientists, et cetera. So it's a full-on multidisciplinary research institute in terms of where our scientists come from and their backgrounds. We have 10 professional staff who work in our education programs and also do our communications and outreach. So it's about 130. I think we're 134 or 5 total staff now. Our headquarters is in Mountain View, California, like 5 minutes from NASA Ames Research Center. And we've been there for 40 years in different locations, but always in Mountain View. But many of our scientists are actually have their offices and laboratories at NASA Ames because of the nature of the work they're doing. Some of our scientists live in other parts of the country, but headquarters is Mountain View. At any given time, we've got about $120 million in active funded research programs ongoing simultaneously. So at the moment, we have over 100 separate research programs that we're leading, and we have another 40 research programs in which our scientists are supporting scientists at other institutions, be they academic institutions or NASA personnel or what have you. So it's a big community that does this work, and it's rarely done in isolation by any one organization. As I mentioned before, about 85% of our funding comes from federal grants and contracts, and the other 15% comes from philanthropic sources. And it funds, the philanthropic sources fund things like SETI, which is depicted in the photograph to the left, which is our Allen Telescope Array, where there is no government funding and hasn't been since 1992, when a senator didn't think the government should spend money on that. The Congress overturned that a year and a half later, but NASA sort of just stayed away and saw this as a political hot potato. So things are changing now again. I think NASA will get back into funding pure SETI programs, but right now those are entirely supported by philanthropic sources. Some of our work in extreme environments is privately funded. Our research is privately funded. We have a gentleman studying the vocalizations and communications of humpback whales, looking at the algorithms and structure of information transfer. That's privately funded. The rest comes from primarily government funds. And of the 85% federal funds, about 85% of that is NASA. The rest is other sources. We also serve as a prime contractor to NASA for planetary protection. This is the science and activity about preventing the contamination of worlds we go to, and also preventing the backward contamination of our planet based on samples or things that we might bring back from other locations. So for example, when a spacecraft or a rover that's going to land on a place like Mars is being built, our scientist goes down and does the biological assays to determine the extent to which the spacecraft has been sterilized or cleaned as much as possible from bringing any life contamination to another world. We oversee an applied machine learning and artificial intelligence research accelerator called the Frontier Development Lab for the Department of Energy and NASA, which is a postdoctoral research program that we take on every summer. Extraordinary work gets done by those teams. We own and operate the Hat Creek Radio Observatory, part of which you can see in the left-hand photograph, and the Allen Telescope Array. These are about 5 hours away from San Francisco in a very quiet and isolated part of California on purpose. We run a project called COSMIC on the Very Large Array. This is, I think, perhaps the biggest and most ambitious SETI program in history. We'll talk a little bit more about that later. The Very Large Array is the iconic array of big radio telescopes in New Mexico that span an area of about 23 miles radius. We administer and manage education programs in partnership with NASA and also the National Science Foundation. We develop formal and informal curriculum materials for education programs for STEM, basically leveraging space exploration and discussions around astronauts and life beyond Earth and things of that sort as a foundation or contextual framework for making education about science more fun and engaging. And we do a lot of public outreach to share our science with everybody. In terms of executing the search, now we can get into how it works, how we do what we do. So there's 3 methods to search for life in the universe. And the first is called in situ instruments, which means basically sending hardware to places of interest with instrumentation on those systems to look for signs of life or precursors to life. And then there's remote sensing, which is observing targets of interest or worlds of interest with technology that can tell us something about the environments or surfaces of those worlds that might suggest the presence or possibility of life. And then the third is SETI, using radio telescopes primarily, but also now optical telescopes looking for lasers, where the idea is that certain technologies in the electromagnetic spectrum can be transmitted literally across our galaxy and theoretically between galaxies, covering extraordinary distances, and be able to be observed by these kinds of systems. And observing a non-natural or so-called engineered signal of some sort, again, would be a transformative moment in human history where we could say, there's not only life, but it's intelligent life and technological life, beyond Earth, whether it's close by or far, far away. So in terms of these methodologies, in situ, again, means in place. So that means sending a spacecraft or a lander or rover to another planet or a moon with instruments for environmental analysis or life detection. That would include things like ground penetrating radar, spectrometers, hyperspectral imaging, camera systems, seismometers, X-ray diffraction systems, gas analysis equipment, drills, probes, you name it, as much hardware as we can fit onto these platforms. That's what we try to do. But this endeavor is essentially limited to our solar system. So, we don't have, as a civilization, the technology to send hardware much further than that. The farthest engineered technology in human history from Earth right now are the Voyager spacecraft, which are just at the very edge of our solar system. So it's about equivalent in terms of what we've sent out into the universe, of opening your front door and taking a look outside and trying to understand the entire planet Earth from your front porch. And in fact, that's an over-exaggeration. So it's certainly interesting work, but it's limited to a very, very small piece of our own galaxy, let alone the broader universe. And then we have remote sensing. And so that's non-contact observation. These would be flyby missions like Cassini around Saturn, or New Horizons that went to Pluto, and now also observing platforms like the James Webb Space Telescope or the Hubble Space Telescope. But in the case of James Webb, this particular telescope, and you'll notice the mirrors are gold, not silver, like a normal telescope. It's optimized to function in the infrared and near infrared and do infrared spectroscopy. And so what it does is, in terms of looking at the atmospheres of nearby planets, if the planet is in front of its star and the light from the star shines through the tiny little limb of the surface of that planet, we can observe the light going through that atmosphere. We can do spectroscopic analysis of that light and determine the composition of the atmosphere and look at the composition, both in terms of what molecules it contains or what elements it may contain, but also in terms of their relative concentration. And we can hope to see if there is something about that atmospheric composition that might suggest the presence of life below. The problem, of course, is it might be very interesting, and we might be inclined to say, I don't know how else this kind of atmosphere could be formed without life, but we'd have to go verify somehow. We'd need other techniques and technologies before we could definitively say there's life on this planet. But nevertheless, it would be an important discovery to say that there's interesting composition in these planetary atmospheres. And I'll tell you that's already happened on a couple of different planets with James Webb. Here again, we have a limit in terms of how far this search can extend, and it's about 20 light years, maybe 30, depending on the planet. But in a galaxy, the Milky Way, which is 100,000 light years across, again, this is a very small area, but nevertheless important and meaningful science. And then lastly, there's SETI. So SETI technology is based on using ground-based radio telescopes and also optical telescopes. And it's all about trying to look for engineered signals or phenomena that are very distinct from what nature produces, or so-called natural phenomena. So radio signals, for example, or laser transmissions, radio signals in a narrow band or even wide band, but with some pattern that we can detect. Laser transmissions, for example, these would be examples of technosignatures. And again, detecting an engineered signal would serve as a proxy for life and intelligence that would be definitive, unlike something from James Webb, where it would be suggestive, but you'd have to prove it. So, and again, the distances potentially are vast. They could be the other side of our galaxy. They could potentially be beyond our galaxy if the energy of the signal was sufficient. And in terms of lasers, just a quick sidebar, because lasers are just something new that we've looked for as we've understood the ability of lasers like radio to transmit energy and potentially information over vast distances. So we have nearby our facilities in Mountain View, the Lawrence Livermore National Laboratory, which has the world's most powerful laser, which is used for nuclear fusion experiments. And if you took that laser, took the output of that laser, bounced it off one of our, say, 8-meter telescopes on Earth, and shined it off into space, it would be 10,000 times brighter than the sun. And it would be monochromatic, one wavelength. So it would be very distinguishable from a natural light source, and again, be something quite indicative. So it's an interesting thing about SETI as an endeavor. You know, we're still a very young, immature technical civilization. If you think about technology having been around for sort of the 100 years since radio was invented. So when we started manipulating the electromagnetic spectrum is probably the time when we can say we became a technological civilization. So that's a very small amount of time. And as we see and observe new phenomena that might be able to be observed from great distances, then we can add those to the list of things to look for. So it's the kind of thing that we can expand our search and our efforts as we encounter new modalities or methodologies of technologies that might be able to manifest across vast distances. So just to give you an idea of the scale of things, this is not the Milky Way galaxy because we can't get this perspective. We're in it, but it's a very similar spiral galaxy to the Milky Way galaxy. And our solar system is located on the sort of outer edge of one of the spiral arms of the Milky Way. And our solar system would be much, 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 much smaller than the little red dot you see depicted there. It would be almost infinitesimally small at this scale because it's not even 1 light year, the size of our solar system. And the Milky Way galaxy is like 100,000 light years across and contains 250 billion plus or minus stars. And what's interesting, we now know, and we'll explain that as well, that in this envelope of just the Milky Way galaxy, never mind the hundreds of billions of others, there's 10 potentially habitable worlds in that space. And I'll explain how it is that we've arrived at that number. But that's a pretty big number, and that's the kind of number that makes the search for life or intelligence, more compelling as we understand that. But again, another quick scale example, the fastest spacecraft humans have ever built is New Horizons that went past Pluto back in 2015. And you may remember the marvelous pictures in the New York Times of detailed surfaces, pictures of the surface of Pluto. And that spacecraft is going at 56,000 kilometers per second. We have other spacecraft going around the sun faster, but that's because they're constantly getting a gravitational assist. But in a straight line, New Horizons is the fastest thing that human technology has ever put together. And if you sent that spacecraft to our closest neighbor, which is only 4.2 light years away, it's a star system called Alpha Centauri, and you can see that star in the southern sky, not in the northern sky. But that spacecraft, to get to our closest neighbor, would take 80,000 years. 80,000 years to get to our closest neighbor, and our closest neighbor, again, wouldn't even show up on the scale of this picture. So it's a big, 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 big universe, and the scales are really hard to grasp. The distances are hard to grasp. So it's just something to keep in mind. So let me talk about and introduce to you something called the Drake equation, which is named for Frank Drake. And Frank passed away just 2022 and was the first president, actually, of the SETI Institute. He was an astronomer also at Cornell with Carl Sagan and Jill Tarter. And he did the very first SETI experiment in 1960 using a, at the time, large, but by today's standards, small radio telescope at the Green Bank Observatory in West Virginia, which is operated by the National Radio Astronomy Observatory. You can go visit it. It's out also in a very remote, quiet area. And it now has the world's largest steerable radio telescope. It's a 100-meter dish the size of a football field that we can point in any direction. But there was a smaller telescope on that campus at the time. And in 1960, Frank Drake pointed it at a star system called Eridani B and listened for radio signals, engineered radio signals. He'd look for narrowband carrier frequencies that might suggest life. And it was based on a paper that a couple of other Cornell astronomers had written a year earlier in 1959. We were realizing after the Second World War, with radio technology and the ability of radio transmission to go great distances and the invention of things like radio and television, that if we had this kind of technology, and based on the laws of physics, which are universal in our known universe, as far as we know, other civilizations, have they arisen, might have the same. And if they did, we might be able to detect them. So Frank did this first experiment. And then a year later, the National Academy of Sciences asked Frank to gather some scientists and scholars together to give a kind of a scientific analysis of the merits of looking for life beyond Earth, at a now famous meeting. And Frank was in charge of putting together the agenda. And he said, well, there are some basic science questions we need to answer if we want to estimate the number of technological civilizations that might be in our galaxy. And if that number is high, SETI makes probably makes sense. And if that number is low, maybe it doesn't. But how do we estimate a number like that? Well, the first is that we would like to know something about the birth rate of stars and the life cycle of stars. How long do stars live? How many stars have planets? Are planets rare or are they common? And if there are planets, might some of them be sort of rocky Earth-like planets in the so-called habitable zone of their host star, so close enough or far enough so that potentially liquid water could be present to allow life to be established. And if there are habitable worlds, in how many cases might life emerge on those planets? And if life emerges, in how many cases might evolution have enough time to develop complex organisms and intelligent life? And if intelligence emerges, in how many cases might a technological civilization come up? So these were the kind of outlined primary science questions, but he added one last question, which has become the most interesting and provocative of all of them. And that was, how long might a technological civilization remain detectable? How long might they last? Either because of their own, the onset of technology brings an onset of challenges, some of which, function as potentially existential threats, like harnessing the atom, or, messing around with pathogens, or messing around with the environment and having an impact on the environment that could ultimately be, lead to the demise of the civilization. So these questions formed the agenda for that meeting. And then Frank realized, well, I can actually put them together into like a formula where the number of technological civilizations N is a function of the number of stars, planets, habitable worlds, the presence of life, the emergence of intelligence, technology, and then the duration of those civilizations. So that was the Drake equation. And I would say that the only thing that we knew anything about in 1961 when this equation emerged was the birth rate and life cycle of stars. Everything else was in the domain of the unknown. But what was interesting is that this formulation sort of put together in a sequence the basic science questions that we need to address if we're going to look for life beyond Earth. So it was not intended to be so, but it became and remains sort of a roadmap for astrobiology and SETI. It is not, of course, a precise scientific formula because we don't know the value of most of the variables, but it gives us a structured framework on which to conduct our work. So this structured approach is behind how we put together the Institute. And so we have essentially one science question: are we alone in the universe? And we divide that into three domains of inquiry: the structure of the universe itself, planets and habitability, habitable environments, and then life and complexity and intelligence. Through these domains, we've set up 6 divisions, if you will, or separate disciplines within the Institute. And these are astronomy and astrophysics, exoplanets, which are planets beyond our solar system, planetary exploration, which is about exploring the planets in our solar system, astrobiology, the study of life in the universe and life in extreme environments, climate, and what we call biogeoscience, the interplay and interconnectedness between life and environment, and then radio and optical SETI. So these are the 6 disciplines of the Institute. And what we do at the Institute, the research involves supporting NASA science missions. So almost every unmanned NASA mission that has ever flown has included SETI Institute scientists as part of the science team. So a lot of work on supporting NASA missions, field expeditions all over the world, laboratory research in chemistry, physics, and biology, ground-based observations using radio and optical telescopes, space-based observations using platforms like Hubble, the Kepler Space Telescope TEST, now JWST, technology and instrumentation development. So, for example, there's an X-ray diffraction system on the Curiosity rover that was designed and built by the Institute that is what looks for it gives you the elemental composition of the surface of Mars, the regolith as it's called. So a scoop goes and picks up material from the surface of Mars. It puts it in the top of the rover through a filter into the instrument, which is a small, compact, very high-tech X-ray diffraction system. And then the X-ray diffraction system can read out the composition of the elements in that soil. So technology and hardware development are also part of what we do. And of course, all the technology behind our radio telescopes is homegrown, including the compute. And ultimately, what we're endeavoring to understand are the structure of the universe, everything we can about planetary environments and their habitability, the nature and origins of life, how it began, under what circumstances, and then the evolution, ultimately, of intelligence and technology. So a day at the office, as I like to say, might include things like supporting the Cassini mission to Saturn, or the TESS mission, which followed on Kepler as a planet hunter. It's a current flying mission that's looking for planets in the entire sky. The Perseverance rover, or the New Horizons mission to Pluto on the far right. We also, again, work on radio telescopes like the Very Large Array. We do work in places like the Atacama Desert, where the tents are located, in Antarctica, in the picture to the right there, on places like the Altiplano of Bolivia and Chile, high altitude areas. And all of these remote locations give us access to information about other worlds. And in some cases, these environments are analogous to, say, early Mars. And they give us an opportunity to sort of travel back in time to look at how life might have emerged and evolved. So that's kind of a day at the office. And in terms of what astrobiology is, astrobiology being separate from SETI, where SETI is focused on looking for technology, astrobiology is looking, for even the most basic forms of life and answering questions about how life began, for example. So how did it begin? How did it evolve? Does it exist elsewhere in the universe? And what is the future of a technological life? So these are some of the basic questions of astrobiology. And ultimately, as noted here, it's the study of the origins and the evolution and distribution of life, equally important, and the future of life in the universe. So it's based on fundamental concepts of life and habitable environments, and all of those also help us recognize biospheres, or environments that might be quite different from our own, but still potentially habitable. So how does life begin and evolve is a key question, and that's really addressed through theory, but also modeling work and laboratory work and field work. And so can we understand environments that are favorable to prebiotic chemistry? How does life start and under what conditions? How does it evolve and survive? And what is the nature of life? And so that looks at the biophysical processes that lead to the emergence of life, but also the coevolution, as we call it, of life and environment. The two influence each other constantly. And also interesting perspectives like Jeremy England from MIT, who believes that life is contrary to original belief, which said life sort of violates the laws of thermodynamics and entropy. His belief is life and biological beings, if you will, biological elements are in fact very efficient entropy engines, and therefore very consistent with the second law of thermodynamics. So interesting questions that come up. So what is life, and is it the result of a universal process? In other words, if star formation is a universal process in our universe, if planets life not be the same. So we do astrobiology as an example. I'm going to let you hear from our director of research, Dr. Natalie Cabral, who she was talking to the Explorers Club in New York a little while ago, and but live from the Atacama Desert, and we recorded that, and I'll let you listen to her here. Hopefully this works. Maybe I have to press, yeah, there it is.
Good morning and welcome to the members and guests of the Explorers Club. My name is Natalie Cabral. I am the director of the Carl Sagan Center at the SETI Institute, and I'm an astrobiologist and a planetary scientist. This is a beautiful morning in Salar de Padranes in Chile. We are in the Chilean Altiplano, and what you see behind me is our base camp. Has been our base camp for a few days now. This is literally a little city behind me. We have about 15 tents, 2 domes, It's an absolutely fantastic landscape. It's otherworldly. We have the feeling that we are actually walking on a different planet, and we have been for several days now. We have a project which is funded by the NASA Astrobiology Institute, which is actually studying ways of detecting biosignatures. It's in support of future missions to Mars, but I mean, in general, it's going to be helping the development of new techniques, new instruments, and new methods of detection for the search for life in the solar system. Salar de Paranales is the first site on our trip. We will stay in the Altiplano between October 27th, which is when the team arrived here, until November 19th. We will be visiting the El Tatio geysers, which are at about 4,300 meters. Here we are at about 3,500 meters at Paranales. And then we'll go even higher. We'll go to Laguna Lejía and Laguna Aguascalientes, all in the San Pedro, the Atacama region. And we will end our trip by climbing the Simba volcano that is close to 20,000 feet. For each of the sites, the goal is the same. We're here to collect a lot of data to understand how we integrate these data from orbit to the ground, to the lab, to develop new detection methods, exploration strategies, and instruments. And with that data also, we are going to be able to train new systems supported by AI and machine learning, which will help us ultimately develop the new exploration strategies, the new generation of exploration strategies for the search for life in the solar system. This project is part of the Astrobiology Research Division of the SETI Institute. It is connected to the mission of the SETI Institute in that it provides us with answers, or at least ways to find answers to, are we alone in the solar system? Basically, what we are doing is to try to understand how to detect life that is not visible or traces of past life that it might be hiding somewhere. I would like to end by first thanking you for having me with you, at least for a short moment. And I am so very pleased that I was able to share with you the landscape we have behind us. It's, as I said when we started, absolutely stunning. And also, I would like to show you the SETI flags that we are deploying. Here is flag number 1. I am always taking it with me. That's the second or third time now that it is deployed in the Andes. Flag number 2 is actually a few thousand kilometers south of here with Dale Anderson in Antarctica. And flag number 3 flew about a week before we left on the Sophia airplane with teachers and Pamela Harmon and Bill Diamond. So thank you very much for having us with you. And on behalf of my team, I wanted to say thank you and goodbye from Salar de Paranales and the Chilean Altiplano. Good night.
All right. So hopefully that gives you an insight to what some of the work looks like for our teams in the field. I'm going to speed things up here because, time is short and a lot of things. But anyway, does life exist elsewhere in the universe? These kinds of questions relate to the existence of other possibly different coevolutions. So the fundamental processes that started life might be the same some other place, but the pathways of evolution and the coevolution of life and environment could be very different and lead to very different results. And you can think about the biodiversity on our own planet and imagine the kinds of different pathways that intelligent beings might follow and emerge from. So from simple to technologically advanced, we have to worry about life as we know it, life as we do not know it, and we develop, again, as Natalie said, the methods and technologies for exploration strategies. Another example about laboratory planet Earth is, for example, using LiDAR equipment on the ice caves and lava tubes in Iceland, which are similar to those same kinds of environments on the Moon and Mars, because these might be the kinds of environments that could form initial shelters for human exploration of these places or the establishment of habitats in these environments. In terms of our expedition field sites, this is just a map which gives you an idea of the places all over the planet where we go, from the North Pole to the South Pole to most all of the continents. And again, these are all related to the kinds of basic questions we have, again, of how does life begin, how does life form and evolve, and what are the tools and technologies necessary to find it. SETI programs at the Institute, I'm not going to spend a lot of time on these, but I think the slide deck might remain available, or that you can go and see and maybe read these slides in greater detail. But it's just to show you an example of the kinds of things that are done. So the left-hand picture is the Allen Telescope Array in Northern California. It's a 42 dish array of 6-meter dishes. And then we have the very large array in New Mexico, which is a 27 dish array of 25-meter dishes. Each one is about 10 stories tall, so that's a very large radio telescope array. And then we do laser SETI programs looking for laser pulses that again would serve as a potential indicator of life and technology and intelligence. So our namesake is endeavor is SETI research, and again uses the Allen Telescope Array and the Jansky Very Large Array in New Mexico. And the Allen Telescope Array was named for Paul Allen from Microsoft, who helped fund it. And it's also a place just like the Very Large Array and the Green Bank Observatory. You can visit these places, and they're quite extraordinary, very interesting. So I'll skip through these, but among the programs we're doing is a survey of the 300 nearest stars to Earth to see if there's any interesting signals coming from them. Called the TRAPPIST system, which is a series of 8 planets around a so-called M-dwarf star, and at least 3 of those planets are about Earth size and in the right distance from that star to potentially be habitable. So 3 habitable zone worlds. So looking at these environments, and particularly looking at certain alignments of the planets with the star, can give us good SETI projects to undertake. Also looking within this sort of ellipsoidal environment of the observable range of the radio telescopes, where the idea is if there are large, massive astronomical cosmological phenomena like supernova or large black holes, et cetera, we can, those might serve as a beacon which would trigger communications and activities through other technological civilizations. So we can use those as another source of targeting. And then we do something called looking for fast radio bursts, which are a phenomena we don't yet understand. They are outside of our own galaxy, and they emit more energy in a few milliseconds than our own sun does in many months. So they're extraordinarily energetic phenomena that emit radiation in the radio spectrum, and we're doing a lot of work to study those. More information about that. Here's an example of a supernova. So on the left, you can see a big blue smudge, and in the right image, taken in that same piece of sky with the Very Large Array, there's nothing there. So this is a star that exploded, and we observed that in the radio spectrum. Here's a planet. I mentioned earlier how James Webb is looking for interesting biomarkers or molecules in planetary atmospheres. And here's one published by a colleague of ours at Cambridge University, discovering interesting things like carbon dioxide and methane and sulfur compounds that suggest possibly the presence of life on that planet. So then a planet like that becomes an interesting place to look at with radio telescopes and see if there's something interesting going on there. So these are all the kinds of things that we do, or looking at the role that magnetic fields play in the formation of stars. We can also look at so-called compact objects like neutron stars and magnetars and other things. And these, again, can give us insights into things like what's in the interstellar medium. Is it because there's stuff there? It's not the vacuum that we all think it is. So lots of interesting research, a lot of collaborations with Oxford, with UC Berkeley, with University of Arizona, Colorado, et cetera. So again, this kind of work is collaborative and involves people from all over the world, and a lot of partnerships. This is a new graphic that was designed for our cosmic project on the VLA. So we're kind of proud of that design that has the partnership entities down at the bottom of it. And ultimately, all of what we're trying to do it's about connecting the dots, because humans break down our natural world into disciplines like chemistry, physics, biology, astronomy, and so on. That gives us an opportunity to try to take a deep dive into some aspect of the natural world and try to understand it. But again, remember, these are human constructs. These are not representative of any division of actual things in nature. And so one of the things we try to do at the Institute, because what we understand is all of these interact with one another. They're all part of a complex system of interaction. So from our point of view, it's about putting the pieces back together. Okay, we understand a little bit about how biology works and physics works and chemistry work. How do they work together? What's the holistic perspective? And can that, can looking at things from a multidisciplinary lens give us insights that the deep dives miss? So that's a big fundamental part of what we do. Where it stands, I like this chart because it's just a star field. This is what you can see in the Milky Way galaxy in the middle of that picture on a clear starry night at a dark sky environment and a good altitude. Thousands and thousands of stars. But the point is that what we now know, these are not just stars that you're looking at. The star is what you can see, but these are solar systems, all of them. Every one of these statistically has one or more planets around it. And this is quite new information and knowledge. Comes from a lesser known, but I think the most profound NASA mission ever launched called the Kepler Space Telescope. And the Kepler Space Telescope was looking at a area of sky. Whoops, let me go back. The Kepler Space Telescope was, let's see, is this animation going to work? Try one more. That's not working for some reason. Let's try one last time. Okay, well, somehow the animation doesn't work, but it basically looked at planets orbiting around stars, and it was looking at 200,000 stars at the same time. And if a planet was in our line of sight and came between the star and the telescope, the light from the star would dim just a tiny, tiny amount, but enough that the systems on board could measure it. And as a result, they were able to, by staring at the same piece of sky for many years, determined that there were planets going around a lot of stars. And yet the statistical likelihood of orbits being in our line of sight is less than 1%. So when you started doing the math backwards, you began to realize that totally by other methodologies, which started in the mid-90s up until the time of the Kepler mission. And the other technologies were really only able to find big, massive planets that had enough of an impact on their host star that we could observe it and determine that these objects were there. But Kepler Space Telescope changed that completely. All the yellow dots are planets discovered by Kepler, and now you can see that many of them were the size of Earth, somewhere between Mars, which would be smaller than Earth, and Neptune, which is bigger. But the vast population is kind of in the sweet spot. Orbital period is on the bottom axis there. So a lot of these are planets that go around their star fairly quickly. But nevertheless, this was absolutely revolutionary information. And now we statistically know ubiquitous in the universe. So it taught us that every star in the sky has one or more planets. The majority of planets are like between Mars and Neptune size, like Earth. About 20% of these are rocky, Earth-like, habitable zone worlds, and that leads to the conclusion that 10 to 60 billion Earth-like habitable zone planets are in our galaxy alone. That goes back to that slide I showed you earlier, and this is how we know that statistic. So what else we learned from Kepler? I think most importantly that this idea of looking for life and intelligence beyond Earth is now more compelling than it's ever been because of what we've learned just in the past decade. So what do we know now? Now we know, of course, about the birth rate of stars. We also know that planets are everywhere. And now we know about 20% of them are habitable worlds. The rest, we don't yet know. So these remain as questions. I like to call them job security. But even if we answer all these questions, it'll just raise 100 new ones. So I'm not too worried. But that's what we know now. And what's the impact of all of this? Why does this matter? And I would say it matters. Well, actually, I'm going to let somebody else say why it matters.
Finding life beyond Earth is no longer a dream. It's a discovery that will likely be made during our lifetime. And it will change everything. We've been here for more than 36 years, at the forefront of a quest that many consider science fiction.
Mars is the closest planet where we might find the possibilities of alien life.
We are home to over 100 explorer scientists.
This just takes your breath away.
Our purpose is singular.
It's kind of best to understand what you have in your own backyard as you're looking up into the cosmos.
To understand the origins and prevalence of life in the universe.
What we are doing is to try to understand, are we alone in the solar system?
Why do we pursue our mission? Because the discovery of life beyond Earth will lay the framework for humanity's next steps to the stars.
We are trying to understand why we even exist.
We are the SETI Institute.
All right, so Morgan Freeman's a tough act to follow, but anyway, yeah, I think it's laying the framework for our future. And you know, when we think about life beyond Earth, you know, it starts on Earth. What we learn about possible alien coevolutions allows us to better understand life and habitability on our own planet and our environment and our coexistence with our environment, and identify habitability thresholds that we should not cross. So that's very important. Astrobiology teaches us to develop a responsible approach to our environment as a civilization on Earth, and perhaps prepare us to become an interplanetary species. And it extends far beyond. So ultimately, it informs an understanding of the future of life as a process in a changing universe. And what it means to be human is also, I think, part of the impact here. So it's about our curiosity. So the search for life beyond Earth really engages human curiosity. And I think, and many of us think, that curiosity is one of the unique traits that makes us all humans, that connects all of the humans on this planet, and it unites us all. And it explores not just the what, like what was that or what is that, but the how and the why. And why do we even exist, as Pascal said in that film? And how did we get here, and are we alone? And a sense of wonder also is part of this. So they trigger wonder and awe when we look at these big questions. They bring us face to face with the vastness of our universe, its unfathomable scale, and they dare to ask the most profound questions in science. So pursuit of these questions inspires us also to develop some of the most advanced technologies ever, and it compels us to explore and to discover and come face to face with ourselves. It's like holding a mirror up to us as we look beyond our own environment. And then ultimately, human nature, we're social beings. We don't want to be alone. You know, many people have this fascination with UFOs that I think tells us much more about human nature than it does about the reality of aliens flying in our space. We want to believe that we're not alone. Most likely we're not, but the quest continues. So lastly, we do STEM education programs. I won't go into detail here, but we have a program that we talked about before, bringing school teachers into direct interaction with scientists on platforms like the NASA Sophia telescope and now ground-based observatories. We have a community college network engaging NASA scientists and our own scientists and others with astronomy teachers in community colleges, which are a great bridge to underrepresented communities to higher education, and help them make these astronomy courses, which are very popular, even better. And then we have a program for the Girl Scouts that we did for a STEM initiative, where hundreds of thousands, I think we're going to cross the 600,000 mark this spring, of girls who've taken badges that we developed as part of the Girl Scouts program. And then we have a very active annual undergraduate summer internship program. Unfortunately, because of our scale, it's harder to get into than Harvard. We have 450 applicants each year for about 12 places. So it's very, very competitive, but it's an outstanding program and really exciting. And ultimately, you know, everything is about excitement and hope and inspiration. And in terms of our public engagement and interaction, you know, what all of these pictures that just scrolled up on this screen have in common is they were all front page images in the New York Times at one point when they happened. So they speak to the fact that we all find these things far beyond our normal ability to see them and engage with them. We find them fascinating and we're curious about them. So our programs, like our radio program and podcast, Big Picture Science, our monthly lectures called SETI Talks, and our Artists in Residence program are all about engaging with the public and bringing different ways for the public to learn about and understand what it is we do. And we, put all of this stuff on the various social media platforms, including now TikTok is there, and lectures. So just like Thorlabs lectures on YouTube, we have a whole YouTube channel with thousands of lectures. You can dive into any topic you might be more interested in. So you can get to know us and get involved if you like, and it all starts with a website. So I encourage you to come and do that. And if you're ever in Mountain View, California, let me know, and we'd be happy to set you up for a visit. It's a fun place to visit. And we'll be happy to tell you more about what we do. So with that, I don't want to overstay my welcome. I'll stop, but I have certainly time for questions if you have time and you have questions. So do I need to do something here, Michael, to stop this, or are you able to do that?
No, I think that we'll just get started with the questions. First, I have some puns to thank you. The presentation was more captivating than a signal from deep space, Bill. It was truly out of this world.
Well, I don't think that's true. If we get a signal, that'll be better than my presentation, but I appreciate the compliment.
Well, up till now, it's true. Seriously, though, thank you for reminding us that the search for extraterrestrial intelligence isn't just science fiction. It's an extraordinary quest that we're all part of. So we do have questions in our queue. And again, anyone who's an attendee, I'd like to invite you to submit questions as well. So there's a lot. We're probably going to take about 15 minutes because we're at a little past 1 o'clock. So we'll see what we can get to. Apologies for those that we don't get to. So first, and I think it's a really fun question to start with, is do we have any protocols in place when and if we do make contact with an intelligent species beyond our solar system? And how will that information be disseminated to the general population?
And it's one we get a lot. And the answer is, there was a kind of a call through the United Nations actually some years ago, but it sort of fizzled out. I think it was because it was at a time that was sort of too early for the technology to be advanced enough where it seemed a likely thing. And now that it seems ever more likely, and as we get closer, we believe, to making a discovery, we're getting more actively engaged in this post-detection question. And in fact, we're starting a post-detection working group at the Institute that includes social scientists, social anthropologists, and as well as scientists. And it's really about, what might the impact be? How should we think about it in terms of, what is the impact of a discovery of an intelligent species going to mean to religions and governments and technology and business and commerce and, the average person thinking about this. So it's something, we're starting to take a more serious look at. There's another group in Europe that's starting a post-protocol detection group at the University of Durham in the UK, but with, again, people from around the world. So it's something that in terms of the impact, we're starting to think more seriously about. In terms of how we will go about sharing the news, the most likely thing that would happen is, the first thing we would have to do is, if we've got a signal that we believe is coming from beyond our solar system and is, unique and engineered and definitely not a natural phenomena, the first thing we would do is get another observatory in another part of the world to look at the same place and see if they see what we see or hear what we hear. Because we would want to verify, firstly, that it is coming, from a great distance. It's hard to get distance scales when you look at something from one perspective on our planet. If we got a verified signal that was way beyond our solar system, we would then probably make an announcement that would be, a joint press release between these institutions. In which we would let the public know. We would let them know only what we know. We wouldn't, make up stories or probably have anything to say about, who sent it or what it might mean about how advanced this civilization might be, etc. We would simply say what it is we observed and where it came from. And, it would make a big difference if it came from, say, within, 100 light years or so, versus if it came from 5,000, 10,000, 50,000 light years ago. That means that whatever transmitted that signal, was thousands of years ago. And we don't know if the civilization that transmitted it, inadvertently or intentionally is even around anymore. But anyway, all we could do is share the facts, and we would encourage public organizations, governments with lots more money, to pursue and follow up on the observation and verify through other approaches what we learned. And of course, discovered there might be something interesting to share with people, like this is a series of pulses or tones or some sort of modulation of a narrowband frequency, and we can share that and let other people. So that's likely what would happen. We wouldn't be able to show somebody a picture of who sent it.
Thanks for that. Also, I think we're getting a little bit of the audio issue again, so I hate to ask, but maybe can we have you turn the camera off. Okay, so the next question is, looking at the picture of your team, it looks like there's an incredible amount of diversity at SETI. Can you elaborate on how this variety of backgrounds and experiences influences the success of the project? Do you have any examples of a time where the diversity directly had an impact on the program?
Well, we're very proud of the diversity of our team, and it was a great observation to pick that out. I had the same observation the very first day I walked in, because we had pictures of everybody on the wall, and I looked and said, wow, there's a lot of women in particular in the institution. And, growing up in the Silicon Valley tech world, that wasn't and isn't the case. We're kind of a poster child, I think, for gender diversity at the very least. And we have people from all over the world. I will say that people of color are still underrepresented in the sciences, and therefore in institutions like ours. But we work hard to change that by working with HBCUs and other institutions, and by working with kids, giving kids equal access to education, so they have the same opportunities at higher education. But about 35% of our scientists are women. The head of research is a woman. The head of communications is a woman. The head of education programs is a woman. Grants administration is a woman. Our machine learning program is run by a woman. Our human resources is run by a woman. So women play a hugely important role in the Institute, and we were founded by a woman. So I think that's absolutely brilliant. And the fact that also people are coming from Asia, from India, from Pakistan, from Europe, from North America, South America, et cetera, also brings different, perspectives, backgrounds, trainings to bear. And so I can't necessarily cite a specific example that says because somebody was of a particular background, we discovered or learned something new or approached it a different way. I would say from our point of view, it's a given. It's not something we marvel at. Oh, this woman or this person from India made this discovery. No, it's normal for us. And our teams tend to be, again, have multiple people. You saw Natalie in the field with a whole bunch of tents. She's got a ton of people out there with her, and they're diverse teams from all over the place. I just think the diverse perspectives and the diverse backgrounds make our science better more broadly. No question about it.
What a great perspective. Thanks for sharing that. We have a question from Ivan in Mexico. He says, kudos for the FDL program in your partnership with Unistellar to foster citizen astronomy. One quick question, besides FDL, are there other programs or initiatives, ongoing or future, to push AI further in SETI?
Yes, well, AI is another great question, and he was asking about the FDL program, which is, again, the machine learning initiative. But we're using AI increasingly in data sets. We have a project we're working on with NASA right now, which is using multispectral imaging to look at so-called volatiles, things like water and other materials on the moon. And the hyperspectral data sets are very complex. And so we're using machine learning and AI to understand those data sets. And then we're taking and expanding that work to in a partnership with the U.S. Geological Survey with hyperspectral image data sets of planet Earth. And, you know, we can't do this work without machine learning and artificial intelligence. Our SETI programs, the data ingest rate at the Very Large Array for our project is 3 terabytes per second. So it's a massive amount of data, and you can't ingest and process data like that without AI and ML tools. And we can do things that we couldn't do before, like we can investigate the radio spectrum in the wideband and not just look for narrowband carriers. And we can, you know, interrogate the wideband, stack millions of images, and look for patterns. You can't do that without AI and machine learning. And so AI and machine learning, in many senses, we think of them as tools. We think of them as new perspectives or new ways to even look at existing data. And I, you know, am often intrigued by the idea that we could be sitting on evidence, or NASA could be sitting on evidence that we don't recognize yet because we haven't looked at it with the right set of tools. So AI and machine learning are playing an increasingly important role in the work we do, and our colleagues in other institutions. Absolutely.
Thanks for sharing that. A kind of a fun question. Have there been any signals that gave staff more than a momentary thrill or chill?
There have been, you know, the problem is that right now we have a computer-generated sequence of analytics that an interesting signal goes through. And then ultimately it goes through human analysis. So if a signal comes in and it goes through, you know, 1, 2, 3, 4, 5, 6, and it still looks interesting, then a human starts looking at that data and trying to understand what's going on. So every time that happens, which is fairly often, it gets a little bit exciting. But, you know, they at the same time, they know that, you know, unfortunately, one of the things we have to deal with on Earth is a very noisy background environment. The so-called radio frequency interference, or RFI, is a huge problem. And, you know, we have to deal with passing airplanes and spacecraft in low Earth orbit, and, you know, Elon Musk's Starlink system, garage door openers, microwaves, cell phones. I mean, everything, all of these things can provide interference that we have to get rid of. So, you know, I think the team is sort of savvy enough to know that, you know, 99.999% of the time, we're going to find that the origin is some kind of RF noise of our own making. But of course, it does get exciting when things go a little further. You may have heard of the WOW signal, which was a result of a radio telescope observation at Ohio State University now many years ago. But in those days, they just had printouts, and, you know, somebody came to look at a series of printouts from something that happened the night before, and there was a string of numbers that he wasn't expecting that suggested sort of some high energy beacon with structure in it from a distant location. And he wrote in the edge of the paper the word "wow!" exclamation point. And from then on, this became known as the WOW signal. Nobody's ever been able to find anything by looking at that same point of sky. And we try that every once in a while, kind of just for fun. So there was probably some other explanation for it, but you know, people got very excited about it. That's for sure. You know, NASA gets an image of something on Mars that somebody thinks looks like a face, or, you know, something else, and people get excited. But nothing that has yet, you know, been, okay, you know, hold the phone, stop the presses, you know, start a press conference. But I look forward to that.
Okay, we're going to have time for just 2 more questions. There's a number of questions around technology. I would expect that from some of the Thorlabs people. I'm going to kind of summarize it as, you know, you brought up LiDAR, spectroscopy, other laser-based technologies that SETI's now using. Are there particular technologies, photonics or otherwise, that you'd like to have access to that would help SETI? And as a follow-up, are there any key areas of technology where you're currently using or would like to use, you know, technologies that are derived from photonics based?
Sure. Well, I mean, photonics is you know, centrally important to the work we do, particularly in observational science. You know, it depends on the kind of work being done. I mean, there's observational instrumentation such as telescopes, and there the most important tools are both the, you know, the sensors on the telescope. In many cases, we don't control what those are or what their capabilities are, but then a lot is around the data analysis. So advanced machine learning algorithms and data analytics techniques are certainly a technology area that we're very interested in, and we partner with organizations that can help us develop new algorithms or new approaches for looking at data. In terms of instrumentation, things like FTIR, infrared spectrometers, GC mass spec, these are interesting instruments. We'd like to have basically access to more of them. I'm trying to fund and build an analytics lab. We have 3 labs at our headquarters at the Institute. One's a geology lab, one's a laser lab, and the other is a instrument lab. I'm trying to add more instruments, including a GC mass spectrometer and gas chromatograph, liquid chromatograph. I mean, all the classical analytical instruments that one finds in various laboratories. Also, even genetic sequencing technologies are technologies that we'd like to put in our analytics lab, which we would then make available to our community of scientists and others, including scientists down the street at NASA or at neighboring universities. So that's a big desire for us, is just to have more on-site in-house capabilities in terms of analytical instrumentation. But yeah, pretty much all of the different ways of looking and observing scientific phenomena through instrumentation and observation are of interest to us. Absolutely.
Great, thank you. It's hard to pick the last question. There's everything from the dark forest hypothesis to what are we doing to send out signals, but there's a number of questions around how do we as a scientific community get involved and help SETI's mission. One person specifically said, they did some SETI work when they were in college. What can they do now as a non-student or non-academic scientist? So could you talk about ways that the scientific community or the general population can get involved and help move forward the mission of SETI?
Sure. Well, one way to obviously for people to get involved is to make donations to the Institute. And I like to refer to donors as truly as investors. And what do all investors want? All investors want a return on investment. And I think the ROI for supporting the work we do or other philanthropic organizations, is the impact of the work that can be done as a result of the gift. And presumably it's the impact on something that means something to the person who made the gift, that I'm really interested in STEM, or I'm really interested in advancing this science. And I know that my contribution, small, medium, or large, is going to have an impact on that. And that's my return on investment. So that's always a helpful way for people to get involved. You can sponsor activities like we have a program. Our undergraduate internship program is partly funded by National Science Foundation, but not entirely. The more funding we can get for students, for interns, the more we can support every summer. And I have such respect for our scientists who work one-on-one with these students every summer. And the funding doesn't go to the scientists, it goes to the students, it goes to house them and transport them and so on. So there's ways like that. We have a council of advisors. And if you go to the website, SETI.org, and look at the About page, and then you scroll down, you'll see things like a science advisory board, the board of trustees, and a council of advisors. Council of advisors is an informal group of people who donate and support our work, but they want to be closer. They want to be sort of insiders. Get updates from me and others on what's going on, and maybe even come up with ideas of their own. We have for online learning programs that the SETI Institute could run. So she's off trying to see if something like that is viable. So the Council of Advisors, is able to support us, be engaged with us, and work with us. But they don't have, the fiduciary responsibility of like a board of trustees. So that's a fun way to get involved. We're certainly always interested in people as well who, are maybe interested in or good at storytelling and have ideas to help us do a better job, conveying our work through social media or other platforms or giving talks. So, or people might say, well, I know a lot about this kind of technology or, this kind of computational data analysis, and I'd like to help. So just, getting in touch with us about that is meaningful. So lots of ways to get involved. And of course, I think it all starts as what kind of impact would you like to have? And, what are your interests? Are they in science or exploration or instrumentation or education or outreach. We can use help in all those areas. Our Science Advisory Board is an extraordinary group of scientists from all over the world. They include the Vatican astronomer who reports directly to the Pope, and he's the guy who's in charge of the Vatican's observatory that's been around for hundreds and hundreds of years. And he's a marvelous MIT PhD astrophysicist and also happens to be a Jesuit priest. The Science Advisory Board is entirely volunteer. They meet twice a year for 2 full days, and they love it because they spend time with each other, and they're all extraordinary. We cover their costs to allow us all to get together, but it's just their passion and commitment that makes them interesting, and that they give us lots of good counsel on what's happening in the sciences, what are the new trends, the new technologies, the new funding directions, et cetera. So there's lots of ways to get involved. And of course, on the FDL program in particular, we are always looking for corporate partners who might want to bring something to the table as a resource, which can include funding, which helps us, among other things, bring in international students. Or it can bring, we have NVIDIA and Google participate, and they provide computational resources. NVIDIA provides GPUs, and Google provides cloud compute credits. And we work with Lockheed, and they provide, data from spacecraft and so on. So there's lots of different ideas, and anybody who's interested in talking more, I would encourage you. You can find out through Michael or others how to get in touch with me, and I can point you in the right directions. But always looking for people who share our passion and want to get involved.
So plenty of opportunities is what it sounds like, and we're hoping to get to partner with you at some point with our mobile learning lab. So
and that would be terrific. I'd like to learn more about that mobile lab, and we'd be very excited about doing that. I mean, again, mobility is another thing, bringing the science, bringing things to all over the country and the world, and especially remote places, and telling our story is of great interest to us. So we'd love to learn more about that and work with you on it. Great.
Well, sorry for the people we didn't get to your questions. This is by far the most questions we've ever received. And honestly, Bill, I wish we could talk for hours. We're probably going to just have to have you back maybe in the spring and summer when there's not going to be a snow emergency.
Well, another idea is, we could do a session that's just Q&A. I mean, I've done these Reddit AMAs, this Ask Me Anything. So there's no talk. There's just, ask away. I do want to say quickly that I don't agree with the dark forest theory, because I think any civilization that has managed to solve the problems like we have with energy, with resource management, with, social justice and all of these things, our civilization, we don't know yet if we're going to make it to our next evolutionary step, because we have so many challenges of our own making that are getting in the way. I have to believe that any civilization that is older than us, which by the way, is the most likely discovery, just statistically speaking, has solved the kind of problems that we're facing. And if a whole society, a whole planet has come together to solve its big existential problems, then it's unlikely, I think, that they're a malevolent society. So this is an area where it's the only area where I would ever dare to disagree with Stephen Hawking, but I don't share that dark forest perspective myself.
I join you in that perspective. Yeah, but that could be a whole webinar and Q&A.
You bet.
I'm holding back as much as I want to go into it.
And just quickly, I'll be, if you guys want to send the questions, we'll try to get, a short series of answers back on them that you can then share. We'd be happy to do that. So I'll leave that to you. But
that sounds great.
Feeling bad when we don't get to people's questions.
Yeah, no, that sounds fantastic. We'll definitely look forward to doing that. But thank you again, Bill, for obviously the presentation, but just the great leadership in one of the coolest, scientific initiatives going on in the world, probably the universe. So with that said, our next webinar will be on March 6th, where we'll have another guest speaker, Dr. Felicie Albert, director of the Jupiter Laser Facility at Lawrence Livermore National Labs. She'll be talking about laser plasma acceleration, the next generation of X-ray light sources. So you can register for this event at our website, which is thorlabs.com/webinars. And don't forget, you can check out SETI, SETI.org, and learn a lot more about what's going on there. So thank you very much for your attendance today, and we hope to see you all again.